Hi everybody. We're back to our fourth bonding lesson at this point. A quick reminder, we are learning about intramolecular bonding. There are three categories of bonds: covalent, ionic, and metallic. We have focused the first three lessons on covalent bonding. I'm going to move on to ionic bonding today. So, it is March 31st. Ionic bonding is our focus. And we need to remember a few things about ionic bonds. First of all, they involve the valence electrons of metals bonding with nonmetals. The key way to describe an ionic bond is that electrons are transferred from one element to another. So metals are considered losers, if you recall, and the metals will tend to transfer one or more electrons to a non-metal. And the electron negativity difference between those metal and non-metal elements are really large differences, and it's greater than 1.6. Okay, so we'll look at a few examples here of ionic bonding. The first one is sodium chloride. Okay, and if you recall, by the way, what I have handy is the periodic table of elements, and I would like you to also have your table S handy. But let's just look at where sodium and chlorine are located on that periodic table. Here's sodium. Here's chlorine. The alkali metals only have one valence electron. The halogens have 7 valence electrons. So these are going to tend to be greedy. And if you recall, the highest electronegative element is fluorine. So chlorine's way up there too. And sodium is definitely going to have a lower electron negativity. In fact, it's going to want to lose or give away an electron. These are going to want to gain electrons. So keep that in mind. So first thing, we do draw our Lewis structure. Sodium has 1 valence electron. Chlorine, as we just mentioned, has 7 valence electrons. And the way we show ionic bonding is I like to draw a little arrow, because that arrow is going to show the transfer of this 1 electron to the chlorine atom. What we end up having here is sodium becoming positive, a cation, chlorine becoming negative, an anion. And if you think about this, sodium becomes like neon. When it loses that 1 electron, it becomes like neon. And chlorine becomes like argon when it gains that 1 extra electron. So as a reminder, all bonding, the goal of bonding is to become stable like noble gases, and this is a good example here. If we look at the electron negativity differences, 0.9 is the electron negativity for sodium, and chlorine is 3.2. So 3.2 minus 0.9 will give us a 2.3 electron negativity difference, which is greater than 1.6, and that makes this also fall under ionic bonding. All right, let's look at another example. This example is magnesium chloride. So when we look on the periodic table, magnesium has forms a +2 charge as an alkaline earth metal, and we're sticking with chlorine over here as the halogen. So we have magnesium with 2 valence electrons. We'll put our chlorines nearby. 7 valence electrons. Let's show that transfer of electrons. So magnesium becomes a +2, and each chlorine becomes -1, and they become stable like the noble gases. When we look at the electron negativity difference, we get a 1.9 difference. And that also falls under ionic bonding because of that. Okay, so a few other things that you need to be aware of with ionic bonds and ionic compounds. Their characteristics are as follows. They have what we call a crystal lattice structure, and that is due to electrostatic attraction. And again, this attraction is because of such a great difference in the desire of electrons. Ionic compounds also exist as formula units as opposed to discrete molecules. So when we talked about covalent bonding, we were talking about molecular compounds. Those are non-metals bonding. They're discrete molecules. Whereas in ionic compounds, we have what we call formula units. This model could represent the lattice structure for sodium chloride. Ionic compounds also have very strong intramolecular bonds. And because of that, they have very high melting points and boiling points. Okay, folks, so don't do this at home, but I'm heating salt on the stove top, and as you can see, it does not melt at temperatures our stoves can achieve. On the other hand, when I heated the sugar, it began to melt and eventually caramelized. Here we have sugar before and after on the left, and salt after heating on the right. Thanks for listening. Bye.